Welcome back to Calculus 1, Class 2, Part 3. Section 2.5, limits at infinity. I think it's sufficient information to start. Limits at infinity. So in this case, we are going to take a look at the problems which have x go to either positive or negative infinity, and the answer could be either finite value or some kind of infinity. So if we experience the situation that you send x to infinity and you end up with a finite number L, which could be, let's say, number 3 or number 7, then you are looking at the definition for horizontal asymptote. So this would imply horizontal asymptote at y equals to L. And if you get one of the infinities, we are talking about the end behavior of a function. So limits at infinity will provide us with those concepts. Of course, the first one is 1 over x because it's always the first one we consider. So let's go with limit x goes to infinity for 1 over x. So if you look at the graph, as x goes to infinity, what is happening with the y value? As you can see, look, observe the dot. What is happening as we are going to infinity? Where is the y value of all these dots going? Goes to 0. So this is sufficient for us to claim that there is a horizontal asymptote at y equals to 0. So we know what the asymptote is, right? The asymptote is the linear line which function is approaching indefinitely. My question to you is, can asymptote be crossed by a function? Yes. Now let's go more specific. Can vertical asymptote be crossed by a function? Can the function go through asymptote? We said yes, and I said correct. Yes, function can go through the asymptote. Can function go, now more specific, can function go through vertical asymptote? No. Can function go through horizontal asymptote? Yes. So we'll have to be a little bit careful, and I will show you through these definitions why and how that actually happens. No, it's due to this one. This one worries about infinity, and it doesn't care, horizontal asymptote, what's happening locally. So if you pierce it locally, it's okay. The function at infinities bends towards the asymptote, where the vertical asymptote was x approaches a value, x goes to 3, let's say. Well, that's local all the time, so it can be crossed at any point. Okay, let's take a look at another function here. How about limit as x goes to infinity for e to the negative x? What do we get here? Depression is kicking in. Help me. 0. Why? How?
Because when there's a negative exponent, then the number gets smaller, smaller, smaller. So if it's infinity, then it'll be 0.
What you said is actually opposite. You gave the right answer, but the explanation is opposite, actually, the way you explained it. There are two ways we can think about this. Well, one way, obviously, is to draw the graph, right? That's the decay graph. And we can see that as we go to positive infinity, it goes to 0. We can also rewrite this as the limit x goes to infinity of 1 over e to the x. Using algebra, negative exponents will push the term in denominator. And now you see that e to the x would be e to infinity, which is infinity. When you divide 1 infinitely many times, then you get 0. Do we all get that concept of dividing 1 by infinity? Okay, we'll get there. Let's do a few more examples of this. So that was another example. And both of these, right, sufficient to say horizontal asymptote at, again, x equals to 0. Remember how in Precalc 1 you memorized that when you have rational functions, if the degree of the polynomial in the numerator is bigger than the degree of the polynomial in the denominator, there is no horizontal asymptote. If they're the same, you remember memorizing all of that? You remember memorizing it. Now, do you actually remember it? No. Why? Because you had to memorize it, right? And you memorized it for the test, and you answered it for the test, and which is the reason why you're sitting now in Calc 1, right? But then, right, it evaporates. It's not like a bike, all right? It's not like a bike. Riding a bike, that's a different concept, right? Riding a bike is different. So now we are going to actually learn the method to solve those problems so that you don't have to remember those rules from before. So what happens if I have limit x goes to infinity of x cubed minus 3x squared plus 1 divided by 3x to the 5 plus 4. Yes? What happened? Nope. Nope.
It's 0.
Yes.
Because the bottom is a lot larger than the top.
Yes. So it is 0 because it's a higher exponent in denominator. But you remember that from the precalculus, which is awesome.
No.
No?
Probably from chemistry.
Oh, from chemistry.
Yeah. I'm taking precalc for like 4 years. So.
In 4, so you're doomed.
Yeah.
Okay. And that went live, so you get the idea. We have it on record. No, that's very good. It is the answer, and actually it is the reason. We are later going to learn the growth rate of functions. So when you have a faster rising function in the denominator, the limit is going to go to 0. When you have a faster growing function in the numerator, then you have infinity, and then if they grow at the same rate, then you have to solve it in some way. Now, what is the cool way to do this? We pick out the largest exponent for the entire problem. What would that be? X to the 5. Okay. And we divide every single one of the terms with x to the 5. So we have x cubed divided by x to the 5 minus 3x squared divided by x to the 5 plus 1 divided by x to the 5. Then we have 3x to the 5 over x to the 5 plus 4 divided by x to the 5. Then we use algebra to simplify each individual term. We get 1 over x squared minus 3 over x cubed plus 1 over x to the 5 divided by 3 plus 4 over x to the 5. And there's nothing else we can do. Now is the time to, again, try and plug in. And if you plug in now, you get 1 over infinity, 3 over infinity, 1 over infinity again, and 4 over infinity. So you get all of these values. Now, what is 1 over infinity? What does it go to? And why? It goes to 0. Awesome. So every single one of these guys is going to go to 0. All of them. But why? Why 1 over infinity goes to 0? 3 over infinity, 4 over infinity. Why do they all go to 0? Yes. Decrease. Okay, very good.
It's going to be so large that we divide by 1. So small.
The answer you get is very small, yeah. So, I mean, I could demonstrate using someone's class prep, but the person would be really annoyed. So all this work and then I rip it. But the idea is, if you take a look, you know what division is, right? Creating physical piles. If you're dividing by 2, you are creating 2 physical piles, and you keep assigning objects until you run out. So if this is number 1, and you want to divide this by 2, it is very simple. You rip it in half, and you will have 2 pieces, right, on 2 piles. Probably your class prep, because you're free. Oh, no?
I thought you were going to do it that.
No, not today. So looking at number 1, or I can have number 4. Here is number 4. I have 4. Oh, number 4, awesome. So number 4, right? And I can just, and I have 2 piles, right? So that's what it means to divide something. Now think about dividing by infinity, because when I divide by 2, this one piece, when I divide by 2, is now this large. It got smaller. If I divide again, it's going to be this big. And you get the idea. So the output that used to be this large is now much smaller. Now, I only divided twice, right? Divided by 2 and divided by 2 again, which is technically dividing by 4. And I got 4 times smaller piece. If I keep doing that infinitely long, each one of these will be smaller and smaller and smaller and smaller and smaller, which means that if you divide infinitely many times, gone, right? So every time you divide a number, a constant, with infinity, you are going to end up with 0, which is the reason why each one of these guys goes to 0. And you end with 0 divided by 3. Which is 0. Now, the rule that you were memorizing earlier in Precalculus was that if the higher exponent is downstairs in the denominator, you will have answer to be 0. Ta-da! I have to unmute the button. Right. Awesome. Now let's take a look at the homework example. Then we'll talk about the end behavior, and we're done. So this is an awesome problem. I mean, my interpretation of awesome problem might be different than yours, but again, let's try to agree to a degree.
6 or 4?
4 on top. Spell it out. All right. So, solving this problem. How are we going to do this? What now? Can't really plug in infinity and be done with it, right? So, this is 4x cubed, right? That's all cool, right? This is the one that. So, what do you think, guys? What should we do? Yes? You started talking and then you lowered your volume below the air conditioning level, and then I just lost you. I tried to tune and get it back, but you started talking good talk. You said divide everywhere by x cubed, and then as soon as you hit the square root, it just disappeared.
16 times x power 6.
Okay.
So square root, apply that to something like 4.
Yeah, but we can't take the square root of it because of plus 1. But that part in the beginning of x cubed was good.
Maybe you could use the English squares beside that, because we...
No, I can't because it's addition. It's plus 1.
Divide everything by x cubed.
Yes, that's exactly what he said. But how are we going to divide it by x cubed for the 16x to the 6? What happens there?
You try and get rid of the square root, right?
Can't because of plus 1. Yes?
You get rid of the square root with the 1/2, just to make it simpler.
Yeah, but it doesn't achieve. It's just a different notation. It still stays the same. We still have it. Can't square because you will be just making it larger.
I think I have it. Can you, what do you call it? Can you multiply the bottom part, like...
Or you want to rationalize. That will just make it worse, actually. In this case. Yeah, that's what he said. It will make it worse. Conjugate, yes, which is rationalizing. Guys, we're going to stick with that divide by x cubed. That's good. Because square root of x to the 6 is x cubed still.
Can you factor it?
Nope. Factors over complex numbers. It's plus 1. Let's divide by x cubed. Let's just divide it by x cubed. You said that. Let's just go with it. It's going to be awesome. I promise. It's calculus. Everything is awesome. Yeah? Yeah. All right, good. I am dividing everywhere by x cubed. I divided everywhere by x cubed. So now, we are going to have 4 plus 1 over x cubed divided by 2 plus, and here is the trick. When this x cubed undergoes the square root, it will become x to the 6. Are we clear on that? When the x cubed undergoes the square root, it becomes x to the 6. Are we all good with that one? So you all know that the square root of x to the 6 is x cubed. If you need to put it back, it has to double up on the exponent. So taking them out, divide the exponent by 2, stuffing them back in, multiply exponent by 2. So now the whole thing becomes, I know algebra is cool, right? And now everything that is divided by infinity is going to go to 0. And what's the answer? 2/3. 2/3. Very good. Square root of 16 is 4. 4 plus 2 is 6. Cancel by 2. 4, 6. Cancel by 2 is 2/3. Very good. Yes? What's the other way to do it? The problem is that you can't look at the horizontal line because computer, you don't know where it is. The highest exponent. Yeah, but this one has two highest exponents and one is buried under the square root. Everything you said is true. You want to look at this one, and that one. And this one is actually 4. So 4 over 2 plus 4 is 6. Yes. Yes. Yep. Yes. Pick values. Pick 10,000, a million, 10 million, 30 million, 1 billion. Right? Because you're going to infinity. And I mean, a billion is nothing. A billion is nothing as you go to infinity. That's, yes. Use the algebra. The way, guys, the ultimate way to solve this problem is to plug it in Mathematica. That's the way to do this. Wolfram Alpha, that's how you do problems. But we want also to show off some of the mad skills in algebra, so we also do it by paper, by hand, I should say. By hand on paper, because we can. Yes?
So what does that mean in terms of the horizontal asymptote?
This means that the horizontal asymptote is at y equals 2/3. Okay, thank you. So what does this mean? We found that the limit as x goes to infinity gave us 2/3. That means that there is a horizontal asymptote at y equals 2/3. So you would draw the x and y axis, and then at 2/3 you would put horizontal line. Then you would set denominator equal to 0, crank all of the rules for the limits to check if there are any vertical asymptotes. Then you would set those, and then you would pick the function in between those. And we are going to have this in chapter 4. So section 4.2 and section 4.3 will be all about graphing functions without calculator. And these concepts, these questions that you asked in the previous section will be back in 4.2 and 4.3 for us to graph functions without calculators. So you will see the awesome absolute value of ln squared x cubed. Graph it without the calculator. And you go, oh yeah, I'm done. It's awesome. That's how it goes. Right now sounds horrible, I know. Yes? So that comes from the algebra. So let's go back to algebra review, and you will understand immediately how this how the step above gets into one on the bottom. So the first idea is that the square root of x can be written as x to the 1/2, as previously noted. Now, if I have square root of x to the 4th, then that means x squared. Why? Because we know that if you have x raised to m raised to n, they multiply. So since we know that square root is 1/2, this means that it's x to the 4th, everything to 1/2, which is x to the 4 times 1/2, which is x squared. So this is what's happening in the background, but in algebra you usually memorize that you are just supposed to divide them, you're just supposed to cut exponents in half and so on. Usually that's what you memorize, but this is the actual work that goes into it using the definition from algebra there. So now if I know that the square root of x to the 4th is equal to x squared, my question is, how much is this? Can I multiply these guys and put them somehow under one roof? I can do that in two ways. Now the first obvious way would be x times x to the 1/2. Now we know that in this case exponents will add, so I have 2 over 2 plus 1 over 2 is 3/2. But that other way is this one can undergo the square root. So how do I write this to have its own square root? Well, I can write it as this. So you see that it picked up 2 exponents because I divided by 2 on the outside, and I still have this one to copy. And now I have a major square root with the x squared times x, which is square root of x cubed, which is x to the 3/2. At which point the applause should be everywhere, because this is some awesome algebra stuff that usually gets, through the cracks, and you don't get to see it. So now this is the one over here that shows you that if this one is to undergo the square root, it must pick up the square. If it's to undergo the 4th root, it must pick up the 4th power. Because think about it, only if you are matching the order of the root and this one, they would cancel each other out to a single variable. So now, if I have x cubed on the outside and I am undergoing the square root, I need to pick up double exponents, because when I want to kick it out, it will lose half of those. So if you want to undergo the square root, it has to go times 2. When it's coming out of the square root, it goes divided by 2. So this was now square root was divided by x cubed, and then I went with a division inside, which means I'm putting in square root over this one, which means I need to double the roots there, double the exponent there. So it picks up 6. All right, awesome. So that is our problem, and that was one of the spicier problems. So that's problem 41. Most of the problems before this one are much cheaper. dd to dx, we did 1 over x. Aha. Hello, inverse trig functions. How are you? Aha. At this point, I will be comfortable with saying I'll give $1,000 whoever like this draws the inverse tangent graph, right? Been around for long enough to do that. So how's your inverse tangent graph going? Yeah, there we go with the. I know. Imagine the formula sheet for everything. you ever learned. By Calc 3, you have a book. Do the first problem in 30 minutes. Don't know any formulas, right? That's why there are no formulas for tests and things. You gotta know the stuff so you can do the next class, and the next class, and the next class, and eventually in 10 years you can do some research. Yes. The one? I'm just asking about the graph now. I just want to know how a graph looks like. Yes. Close. You want to go and draw it? Yeah, no. Catch the marker, it's like plus 1 point. Oh. Ah. Soccer. Oh, you're a soccer player? Yeah, you should. All right, next time I will. Next time I will kick it. Why? You said so. Nope, those are the sines and cosines. Inverse sines and cosines. Depending on where, how it goes. You got it? Let me give it a try. You want to try to remember? All right. Your next line? All right. And then you see the boss. Ah! There we go. That's the one.
5 points, right? My class.
5 points? 6 points. 6 points. Oh no, you didn't catch the marker.
Oh.
2 points. Yeah. All right. Wow, look at that one.
Yes.
It's like the eye exam.
Yeah.
All right. Because one time I saw this beautiful, beautiful, vibrant orange dry erase marker, and I went for it. It was like invisible ink. So, after some deliberation here, we're back streaming now. Well, it was streaming all the time, so everything is on. We have that the graph looks like this. We have these two horizontal asymptotes, and then it looks like this, inverse tangent graph. So what's the value of the upper? Pi over 2, very good. Clearly, horizontal asymptote at y equal pi over 2. So this was a good exercise actually, because the graph on the left on the board is depending on how precise you draw it through the origin, whether it goes through 0 or goes through 1, is either inverse sine or inverse cosine. And the one on the right is inverse tangent. So we just reviewed all of those in once. Now I want to ask one more thing, and that is, what is the limit for e to the x as x goes to infinity? Yes? Nope. It's not 1. What is it? Yeah, what's the limit of e to the x as x goes to infinity? Nope. Not 0, not 1. Infinity. Yeah. Oh, you said infinite. Yeah, infinite. Okay. So it is infinity. Why? How? Well, if you look at the graph, as x goes to infinity, you see that y tends to infinity. So now something like this would be considered the end behavior of the function, meaning whether it rises or falls to infinity as you go to infinity. Now, these things are very important in terms of analysis of your solutions for, let's say, differential equations. We know, maybe, well, from precalculus, maybe you remember it. In chapter 3, if you took precalc here, with our chili pepper book, in section 3.5, we talk about the exponential models and we talk about population problems. And you might have seen and worked with the population model which looked like this. Population and time is equal to initial population time e to the kt. Now this function is exactly the graph above. This is your initial population P0, this is your time axis, and this is the population axis. So you see that the population grows exponentially as the time goes on. Now when you solve a certain differential equation, you get to see this, this model. And then what do? You want to check the validity of the model, because you have to understand this, guys. Every single formula in physics was derived through differential equations. Every single one of them is a solution to a differential equation. So if you are observing, let's say, this phenomena here, this is a solution to a differential equation which came from the word problem, and the word problem said this. Change in population is proportional to population. That's all you need to say. From there you write the differential equation, you solve the differential equation, you get this as a solution. And now this is supposed to model population. Now in our chapter on limits, we say, well, let me see how good this model is. So you say limit as time goes to infinity of P0 e to the kt, and then you say, if I wait infinitely long, I will have infinitely many people, which we know should not be good because our planet has finite surface with finite resources, and we're technically almost there, all right? Depending on which school of thought you observe, the carrying capacity of this planet is going to be anywhere from 10 to 15 billion, depending on, right? And we are at 7.4 now, which doubled in last 20 years, I believe, 25 years. So 25 years ago, the population of this planet was half of what we have today. So we are experiencing insane population crisis on the planet right now, but no one is talking about it. It's just, we swipe it under the rug. And looking at this model, we see that that is not a good model. But we use the limit, which is what we are learning now, in this concept of the end behavior of the graph. Because you want to see at the end, which is this t goes to infinity, what is happening with the model, and if the model is a good predictor. We have to be aware of the situation that even if we have another planet, the population issue will still be there, because exponential growth is fast growth. And we'll tackle this little bit of this story later on in the course. So now when we are talking about end behavior is looking into what's happening at these ends of the graph. Now we know that this end over here is experiencing horizontal asymptote, right? That's a horizontal asymptote there. And one interesting aspect, guys, of this particular one is that you are looking into the limit x goes to negative infinity of p0 e to the kt. Now look at this. And you remember the previous example when I had e to the negative x going to positive infinity. See, that negative came either from the function or from the limit part. But exactly one negative, it's a horizontal asymptote because it goes to 0. If there is no negative, in this particular case, it goes to infinity. So this one is horizontal asymptote behavior on one side and the end behavior of going to positive infinity on the other. You can have 4 end behavior pieces, and you can quickly find all of them, obviously. I don't know why I put these arrows, because I'm just trying to make a chart, actually. So give me a second to undo that. So we can have a behavior like this, a behavior like that, a behavior like this. So if they go onto sides like this, so let me give you an example of parabola, both up, cubic or tangent, up and down, right? You can have the negative to the x to the 4th minus 1, looks like this, right? So you can have all of these different things. They can have combinations, so all of these have the end behavior, and then you have the combinations of asymptote with, right? So this is the e to the negative x, and so on. So now this one over here is the limit x goes to negative infinity of f of x producing positive infinity. This one is limit x goes to negative infinity, of f of x producing negative infinity. This one is the limit x going to positive infinity of f of x producing positive infinity. And this one is the limit x going to positive infinity of f of x producing negative infinity. It shouldn't be that hard to figure out, because you see that the arrow goes to the right and up. Both infinities are positive because you want to go this way to positive infinity, right? Let's put the arrow. So this way is the positive infinity, this way is the positive infinity, this way is the negative infinity, and that way is negative infinity. So there's too much clutter over here, so what I'm going to do is I'm just going to box this one. Let's not be too dramatic. So this is your end behavior of the graph. Not a big deal, right? Not a big deal to solve problems, but then it is actually very big deal when you start working and building things later on. We're done. 2.5 is done. You either have the end behavior as you send to positive or negative infinity, if you get infinities as the answer. If you get a finite number, you have a horizontal asymptote. So stop the stream. We're going to hit the break.